In this video tutorial, I'll investigate a thin-walled cylindrical pressure vessel with spherical end closures and how the von Mises stress varies by changing the thickness using a design sensitivity analysis. So I've already selected my units as newtons, millimeters, and seconds, and material is low carbon steel. So I'll select the XY plane to start a sketch where I'll create a cross section of this vessel that we looked at in the class and define our 2D axisymmetric model. So this is the wall of the vessel in this straight part, which is 150 millimeters long and 100 millimeters inside, and originally has 5 millimeter thickness. I can use a construction line to define the arcs that will be the spherical enclosure. So we can click on construction mode, create line, and then from that point to the center line, and that allows me to pick a point here when I define the arc. So I exit the construction mode, define center and ends, so I can easily pick the center now and the starting point and the end point of the arc. So this is the inside surface definition for the arc, and I also want to do another one to define the outside surface. And I can create another line to define a closed sketch. I'll need to delete this line, so I can go to delete segment, delete, and when I click the middle mouse button, I've got a completed sketch. So the internal radius of the end cap is 100 and outside radius of the end cap is 105 millimeters. And that is something now I can use to revolve this vessel. So if I say OK, it's asking for where do you want to revolve it. It's the y-axis. So this now shows me half of the vessel as a 360-degree revolution. But I only need to show 90 degrees and say OK. So if I use this solid model, for example, on the XY plane, this surface can be used as the basis of the 2D axisymmetric model. So now I can go to application simulate and then analyze this. But because this is going to be a design sensitivity study, I want to make sure that the thickness can be driven by a parameter. So to define the parameter, I can go to model intent, parameters, and press plus to define my thickness parameter. Let's call this thickness 1, and initial value is going to be, let's say, 5, and press OK. Now we can assign that parameter to one of the sketched dimensions. So if you go to section and edit that section, the thickness can be defined as a dimension. So I can add it here. So that should be 5. But if I wanted to use a parameter for this, I just need to enter thickness 1 there, and then it will ask me, do you want to add this relationship SD4 equals thickness 1? So I can say yes and OK to that, and that is my vessel defined with a parameter of thickness 1. I can go back to my model intent parameters and, for example, change that, let's say, to 20 and press OK. And the model doesn't update immediately, but if you notice, there is a regenerate option now available, so I can regenerate this model, and you can see that the parameter is now applied to the sketch, and I have revolved a thicker vessel. So let's take this parameter back to its original value, 5 millimeters, and press OK. Again, regenerate to go back to our original geometry. So the idea is to vary this thickness parameter from 5 millimeters to 10 millimeters and look at the effect of the thickness on the von Mises stress on this pressure vessel. So now I can go to Applications, Simulate, and define my idealization. Because on this case I want to use an axisymmetric model, I need to go to Home, Model Setup, Advanced, and 2D axisymmetric. The Cartesian coordinate system is part system definition, and geometrical reference is the surface, which is this, which defines the cross section of the vessel. So confirm that, and there is a purple outline that defines my 2D axisymmetric surface. So next step is to define the boundary condition, and in terms of displacements, the only boundary condition that's really necessary is to apply a displacement of 0 in the y direction on that line. So if I free the x direction on that line, that means the vessel is free to expand radially. But if it is fixed in y, the vessel is going to be fixed actually at that cross section at the bottom. So if I say OK to that, the next bit is to apply a pressure, and that is going to be applied on the internal surfaces. So let's say if we try to select these pressure surfaces, of course you'll find that you can't select it because this is an axisymmetric model. You'll need to select the edges that defines the internal surface for the 2D axisymmetric model. So the value of the pressure I want to add is 10 megapascals. I can preview that, and that looks OK, and press OK. So my displacement boundary condition and pressure is applied, and therefore my model is ready to solve. But I can go and refine my model a bit more by adding a maximum element size. Because these are P elements, I can leave it to the default and use the adaptivity to make it converge, but it also helps if I add a maximum element size. For example, if I do add an element size of 10 millimeters and press OK, we can look at what it looks like in terms of elements. So it created just about 73 elements there. So they are one element through thickness effectively in most of the cross section. But remember that these are p-type elements, and each of these edges can be up to 9th order polynomial to represent the variation of stress through the thickness of this vessel. So that's probably quite adequate for this simple vessel. We can close that and save the mesh, and next we are ready to solve this model. We can go back to Home tab, Analysis and Studies, and we need to define a new static analysis, and using constraint set 1, load set 1, and multipass adaptive, maximum 9th order polynomial, and 5% convergence. That's fine, and I can start this and see how the solution looks like. That is essential to have an analysis done before doing a design sensitivity analysis, because that will be reliant on this analysis that you have just completed. So if we now go to look at the results, if we just do OK and show, that is the von Mises stresses, and 188 megapascals is the maximum. The maximum principle is the hoop stress, and you can see that on the cylindrical portion the hoop stress is about 200 megapascals, and on the spherical portion of the pressure vessel the hoop stress is about 88 megapascals. So you can verify that by using dynamic query. So that's about 95 here, 98 on the inside surface, so about 100 megapascals. And on the cylindrical surface, on the inside surface, it's about 203, outside surface just slightly lower. So there is a small variation from inside surface to the outside surface. And what you'll need to do is use the thin wall shell theory, thin wall pressure vessel theory, to look at what is a theoretical stress for the spherical bit and the cylindrical bit of this pressure vessel. One thing you can do to help you with that is to create a graph. For example, if we create open analysis 1 and create a graph, and we can do that graph, let's say, of the hoop stress, which is the maximum principle in this case, and we can do a graph relative to the curve arc length, or it could be the y direction, but let's try curve arc length and click to select a path for this. So on the inside face I can select these two edges and click OK, and it asks me where do you want the starting position for this graph, and at the middle of the vessel is fine, so I'm going to plot the hoop stress from that point up to the end of the pressure vessel as a graph. So if I do OK and show now, it will show me how the hoop stress is varying from the middle of the vessel, so it's about 200 megapascals there, and as the inside surface is at the top, you can see that the hoop stress is dropping down to 100 megapascals. What you'll need to verify these numbers with is PR upon T for the cylindrical portion and PR upon 2T for the spherical portion, as we discussed in the lectures. So that is the analysis completed, and the next part is to define a design sensitivity study. So we can close these views and go back to our model, and now we need to add a new design sensitivity study. So this will use analysis 1 and also use the thickness, which is going to be one of the parameters from the model. So I can select this thickness, and clicking strain will add that to my sensitivity design study, and already it has selected 5 as my current value for the thickness, and I want to change that from 5 up to 10 millimeters, and I want to use 10 steps. So it will use analysis 1, a static analysis, and it will vary the thickness 1 parameter, currently 5 millimeters, but starting from 5 and ending at 10 millimeters for 10 steps. So that will change the model in 0.5 millimeter thickness increments. What you can do is, if you go to options, it is possible to do a shape animation of the model. So you could, for example, continue to step 2, click to say yes, 3, 4, etc. So you can look at how the parameter changes and how it is affecting the shape of the model. And at the end, it is asking me whether you want to restore the model to its original shape, and I say yes, so it's going back to original shape. Another point here is the repeat p-loop conversions and also remesh after each shape update. You could tick these if you think that the geometry of your model is going to change significantly, and that recalculation of the p-loop conversions or remeshing would help accuracy. You could click these. In this current one, I don't need that because the shape isn't really changing that much. So I can close that, and that is the definition of my sensitivity design study. So if I press OK, and I can start this design sensitivity study, I say yes to override run interactive diagnostics, and it's a relatively small model, so it should finish fairly quickly. But what you might find is that if you are looking at a large 3D model with many solid elements, for example, and complex stress variations in the model, which requires high p orders, you might find that this will take significant amounts of time, especially if you're asking for too many steps. So initially start with a low number of steps, make sure your analysis works okay, and then look at increasing the refinement of your model. So for study 1, I can look at the results, which will tell me as a graph how a measure changes against my design variable. So my measure, that's the only option here, is one of the global predefined measures, and I just want to use the maximum von Mises stress, which is max stress VM, and these are my predefined measures. You can also define your own measures and then check how that changes with a given parameter. So press OK. So if I click OK and show now, that will show me how the von Mises, maximum von Mises stress on the model changes when I change the thickness of the wall from 5 millimeters to 10 millimeters. So it has ran this analysis for 11 times. That gave me 10 intervals, and I can see that as the thickness is changing from 5 to 10, the stress on the model is nearly halved. So it's more or less a linear variation, but at the end it is just slightly over 100 megapascals in the model. So what we can do as an investigation, interpretation of this is, if for example my vessel's design stress is given as say 150 megapascals, and that it shouldn't exceed that level, I can look at this graph and select a thickness value that will satisfy that condition. So 150 megapascals at this level, if I read off from this graph, is just over 6.4 millimeters. So for this pressure vessel, if I chose 6.5 millimeters for the radius, I will be able to satisfy my design condition of 150 megapascals. So that concludes our design sensitivity study, and in the next video we'll be looking at design optimization, where we can do this type of evaluation automatically using Creo Simulate.